Hello, I hope I am audible. I am Gaurav from MS17 batch. The topic of my term paper presentation is quantum phase transition. But before diving right into the quantum phase transitions, I think we should review the theory of phase transition because we certainly don't know about the phase transitions as we think we do. So phase transition on a fundamental level can be thought of as a tug of war between the kinetic and potential energies, where kinetic energy on the one hand tries to make the system more disordered, and the potential energies tries to establish the order in the system. As we can see, the disordered state is more symmetric than the ordered state. And while we go from a disordered state to an ordered state, we can always find some quantity in our system that can help us measure the amount of order and that quantity is called the order parameter. And based on how order parameter changes as we pass the critical point, the phase transitions can be classified as first order or second order phase transitions. This is the typical phase diagram of a ferromagnet where magnetization is the order parameter, and we can see that the transition from a ferro down to a ferro up state, the magnetization has a discontinuous jump. So this transition is a first order phase transition, whereas the transition from a ferromagnet to a paramagnet, the magnetization changes continuously. So this transition is a second order phase transition. But the main thing is we need to talk about is the physics near this second order critical point is full of surprises. The first surprise we might have got in our high school, that the distinction between the two phases in the vicinity of this critical point vanishes. And the second surprise is the thermodynamics fails in the critical region. In this region, thermodynamics fails. Why, one might ask? It's as usual, the interactions which we might have ignored while developing a theory of thermodynamics have come to see us now. So basically what happens is that the extensivity property of the thermodynamic potentials fails as we approach the critical point. So how do we study physics in the critical region? So it's also as usual, the nature comes to a rescue, and or we should say the big minds who decode nature. And the big properties of the systems in the critical region emerge. The first is the universality. It means that the wide variety of systems which differs widely from each other in their interactions, in their interactions, and the macroscopic properties start showing the similar type of critical behavior. Like for example, the van der Waals gas and the Ising ferromagnets shows a similar critical behavior as we approach the critical point, and this leads to grouping of these things into the classes, which into the universality classes, and we are familiar with the Ising class. Then another example can be a Heisenberg class. And the second property which emerges is the scaling, which means that the homogeneity again comes out as we approach the critical point, but this homogeneity is different from the first order homogeneity which we know in thermodynamics. So how do we explain universality and scaling? It is clear that the interactions are no longer the deciding factor because the widely different type of systems are showing the similar behaviors. One might guess that the symmetries of the system Hamiltonian are at play here, and this is what explains the universality. And the scaling can be explained by the correlation length. As we approach the critical point, the correlation length, which measures the scale over which the interactions are prevalent, and the scale over which the local interactions are prevalent, diverges as one approaches the critical point. And at the critical point, the interactions of the system, the local interactions of the system are spread over the whole space. spread over the whole system space. And another property is so we can say that the system becomes homogeneous in interactions as we approach the critical point rather than the homogeneity without interaction that we had in thermodynamics. The another property which we encounter is that the interactions slow down in time. Apart from spreading out in space, they also the interactions between the particles also slow down in time. So the basic theory of critical behavior, like the physics near the critical point, can be summarized by the critical exponents, which encode the variation of the different order parameters in the critical region, and this is the homogeneity law or the free energy density in the critical region. And we can see that here the D is the dimensionality, and we can see that this uh, the the physics of the critical region is highly dependent on dimensionality of the system we are studying. And these two laws can be explained by, and these two things can be explained by the Landau-Ginzburg-Wilson theory and the renormalization group theory. Now we are ready to dive into the question of quantum phase transitions. So all the phase transitions that we observe in a daily life are governed by the temperature-induced fluctuations in one way or other. Whereas quantum phase transitions are the phase transitions which are governed by the quantum fluctuations. But we know that the quantum fluctuations are very small, and they are usually hidden. Hidden or dispersed by the temperature-induced fluctuations. To know the region in which the quantum fluctuations will be important, we should compare the relevant energy scales in the two regions, that is kBT and h cross omega. And I have shown in my term paper, and it is also easy to guess, and I have shown in my term paper theoretically that the quantum fluctuations become important only at absolute zero. And this is the typical phase diagram, near the quantum critical point. And here this dotted line separates the region of dominant quantum fluctuations from the dominant critical fluctuations. And P is some non-thermal parameter that is varied to bring about the quantum fluctuation. And this solid line separates the one phase from the another, which means this is the line of the critical temperatures as we vary some non-thermal parameter of the system. This blue region is the critical region, and we can see that the classical we can see that asymptotically near this line of critical temperature, it is the classical fluctuations that are deciding the critical behavior. So the quantum phase transition can only be brought about in the temperatures that are very near to the absolute zero, such that the classical fluctuations become so small that they no longer contribute. This is also the quantum fluctuations can also be brought about in this way, but I will talk about this later. These are the homogeneity law, and the homogeneity law for the quantum phase transition can be generalized, and it acquires this form. And by comparing it with the classical homogeneity law, we can see that the quantum we can conclude that the quantum phase transition of a system in d dimension is equivalent to a classical phase transition of d plus z dimension, where z is some dynamic critical exponent. This fact turns out to be very important in the mean field theories, in the mean field theories. And another change we can notice is that there is a temperature here, and this introduction of temperature actually explains why we can have a quantum phase transition in a region directly above the critical point. This is due to the fact of quantum scaling. I have discussed about this in my term paper. I think I can talk about this. Yeah, so basically what happens is that the free now I can talk about some real examples of the quantum phase transitions. The first example I want to talk about are Wigner crystals. So Wigner in mid-1930s proposed that the electrons in the appropriate condition can form the stable structures like a lattice formed out of electrons, and these structures are called the Wigner crystals, and these can be realized in the um, on the surface on the like in the uh, two-dimensional uh, semiconductors or on the surface of a liquid helium. And to bring about a quantum phase transition in this case, what we do is if we start confining the system to a lower and lower dimension, and we start applying pressure on the system and start applying pressure on the system and start compressing the system, the Heisenberg uncertainty principle kicks in, and the fluctuations in the kinetic energy of these Wigner crystals become larger and larger, and eventually eventually after some critical point this crystal melts to form a Fermi liquid. This is like a this is like a classical phase transition. This is like a classical phase transition of a solid to a liquid. And because we can see that the electrons are not allowed to move in this system, this is an insulator and this is a metal, the Fermi liquid. So this is also an example of an insulator to metal phase transition. The next example that I want to talk about is the quantum Ising systems. The Ising systems are the one in which the spin of a system, the spin at each lattice point can take only two values along the spin axis, up or down value. And we know about and we do about the ferromagnetic systems, a ferromagnetic phase transition in which we increase the temperature and the fluctuations in this spin become larger and larger, and at some point the ferromagnet loses the loses its magnetization as and becomes a paramagnet, as shown in this critical diagram. That if we increase the temperature from here to here, the ferromagnet will eventually become a paramagnet. But this same transition from a ferromagnet to paramagnet can be brought about if we apply some transverse, means the field perpendicular to the spin axis of this system. Uh, uh, yeah, the spin axis of the system, the fluctuations in the the spins starts fluctuating between the spins starts transiting between the up and down values, and there is a super and at each lattice point there is some superposition of the up and down states with some probabilities, and after some critical point at c of the magnitude of the transverse magnetic field, the system loses its magnetism and again become completely disordered. And this is also a paramagnetic state, but this paramagnetic state differs from the thermal paramagnet, as in this paramagnetic state each lattice point is the superposition of the quantum wave functions of the spin up and spin down states. And the properties of the quantum paramagnets are also different from the properties of the thermal paramagnets. So the next example is high temperature superconductors. I think I have talked a lot, and you can refer to my term paper for this. Thank you.